Hello friends, welcome back to my channel. Today I'll be discussing equimolal counter diffusion of two liquids. This is a continuation of my discussion on molecular diffusion in liquids. This will be the third video on molecular diffusion in liquids. In my first video on the topic, I had talked about how Fick's first law of molecular diffusion can be applied for liquids. And then there I told you, uh, as far as purely physical separation operations are concerned in chemical engineering, two cases are very common. One case is component A diffusing in non-diffusing second component, and the second case is equimolal counter diffusion of two components. So we are talking about liquids. In my previous video I had discussed the first case. That is the case when liquid A diffuses in non-diffusing liquid B or stagnant liquid B. The second case is the topic of my discussion for today. So I will be discussing how to get an equation for finding out rate of diffusion through a binary mixture when there is equimolal counter diffusion of the two components. Okay, so let us start the discussion. So title for my discussion is this is continuation of molecular diffusion in liquids. As I said, molecular diffusion in liquids, and today I'll be talking about steady state equimolal counter diffusion of liquids A and B. We are going to consider a binary system where there are two liquid components, component A, liquid A and liquid B, and there is steady state equimolal counter diffusion of liquids of these two liquids. So for this case, we will be finding out an equation, or we will be getting an equation to find out rate of diffusion of A and then rate of diffusion of B. And this is my brief introduction to you. This is me, and I have been preparing videos on various aspects of chemical engineering, and I'll be doing it in future as well. Various important aspects of chemical engineering I will be covering in my videos. You please subscribe to my channel, hit the bell icon so that you will get notified as soon as I upload any new video. Please tell your friends to subscribe to my channel. So let us start the discussion. So this is equimolal counter diffusion of liquids A and B. For equimolal counter diffusion, what is the meaning of what we mean by equimolal counter diffusion? In equimolal counter diffusion, if you talk about equimolal counter diffusion of two components, then these two components have the same rate of diffusion, but the direction of diffusion is exactly opposite. The two components are diffusing at the same rate but in opposite direction. So this has to be understood. So in equimolal counter diffusion, what is this case? Rate is same. Rate is same, but direction of diffusion is opposite. Direction of diffusion is opposite. Okay, so that means if you, for these two components, if component A is diffusing in this direction, that is from left to right, then component B will be diffusing at the same rate but from right to left. Okay, so this is when this happens, we say that there is equimolal counter diffusion in the solution. Okay, so for equimolal counter diffusion, the rate of diffusion is same, but the direction of diffusion is opposite. So this is how you can represent it pictorially. Okay, so let us continue. Let me first erase this. So I hope now it is clear to you what happens in equimolar counter diffusion, or what is equimolar counter diffusion. Okay, so for how to represent this mathematically, it will be represented by a simple uh, relationship. There is a simple relationship between molar fluxes of the two components. Na is equal to minus Nb. Na magnitude of the two fluxes is same, but direction is opposite. The direction is indicated by presence of a negative sign in the equation. So in short, for equimolar counter diffusion, Na is equal to minus Nb. Further, we are considering this equimolar counter diffusion at steady state. So what is the understanding of this? At steady state, the two fluxes are constant. They are not changing with respect to time. At steady state, molar flux of A and that of B are constant with respect to time. They do not change with respect to time. Okay, then we will start with the discussion. For this discussion, we will start with this equation. What is that equation? The equation is for the molar flux of A relative to a fixed position in space. So when you measure the molar flux relative to a fixed position in space, you are measuring n type of molar flux. That molar flux is n type of molar flux. The other is j type of molar flux, which I'll just show you what is that molar flux. Okay, so for time being, how is n type of molar flux for A given? It is given by this equation. Na is equal to n into xa plus ja. What are the terms involved in this equation? N, capital N is representing the total molar flux, which is addition of molar fluxes of components A and B. Then small xa, it represents mole fraction of A in the mixture. Ja, the other type of J type of molar flux for component A. This is molar flux of A relative to molar velocity of B. Okay. So N type of molar flux for A, it has two components. One is the J type of molar flux, and the other one is that fraction of total molar flux which is due to presence of A in it, which is due to diffusion of A. Okay, so I hope this equation is clear to you. Now let us move ahead. For a binary mixture of A and B, when there are only two components, the total molar flux is given as N is equal to Na plus Nb. Simply addition of the fluxes of two components. Then in my discussion on Fick's first law applied to molecular diffusion in liquids, I had talked about the equation that I am going to show. So for molecular diffusion of liquid A in liquid B, Fick's first law, mathematical expression for Fick's first law is like this. Ja is equal to minus dAb rho upon mw average dxa by dz. I have discussed this. I am giving links to those videos in which I have discussed all the concepts. You please watch those videos. This equation will be clear to you. Okay. So you have the mathematical expression for Fick's first law is like this. Ja is equal to minus dAb rho upon mw average dxa by dz. So next, what I'm going to do, I will use equation for Ja in this equation. So you have got equation for N, and then you have got equation for J. So we will be using these equations in the first equation, in the equation for Na. So in place of N, we will be writing Na plus Nb, and in place of Ja, we will be writing this equation. So that's why you get this equation. Na is equal to Na plus Nb into Xa minus Dab rho upon Mw average into Dxa by dz. Okay. Now on the next slide, after this, what we will do, we will use for equimolal counter diffusion, the relation is Na is equal to minus Nb. So we are going to use that relation over here. That is, in place of Na, we will use minus Nb. And then let us see what happens, how the equation gets modified. Okay. So from our previous discussion, where Na and Nb are related through this equation, Na is equal to minus Nb. Equation for Na then becomes Na is equal to minus Nb plus Nb into Xa. You please note we have replaced Na with minus Nb. So Na is equal to minus Nb plus Nb Xa minus dAb rho upon Mw average into dXA by dz. Next step is you can straight away tell this term will become 0. This term will become 0. The reason is minus nb plus nb is 0. That's why this will become 0, and you are just left with this short small equation. Na is equal to minus dAb rho upon Mw average into dXA by dz. And the next step what I do, I'll just separate the variables. You have two variables xa and dz. So I'm bringing dz on the left hand side of this equation. So I have Na into dz is equal to minus dAb rho upon Mw average into dXA. So what can you say about this equation? I'll call it as a star equation. What can you say about the star equation? It is a differential equation. It is a differential equation that describes how Xa is changing with Z. So as you move along Z, how Xa changes is given by this particular differential equation. Okay, so we will understand this with the help of concentration profile for A. So let us show the concentration profile. You have one plane and you have the other plane. This plane is Z is equal to 0 plane. This plane is Z is equal to Z plane. At the plane Z is equal to 0, concentration mole fraction of A is Xa1, and diffusion is taking place from this plane to the other plane, that is Z is equal to Z plane, where mole fraction of A is Xa2. Okay, so uh, how you can understand the concentration profile as you move from the plane Z is equal to 0 to Z is equal to Z, concentration changes along a straight line. Concentration drops along a straight line. Are you understanding this? So I hope this is clear to you. So from this particular concentration profile, you can write these conditions. That is, when Z is 0, Xa is Xa1, and when Z is Z, Xa is Xa2. Okay. So we are going to use these limits. We now have understood the limits which we can use to integrate the differential equation that we had got. So limits are at Z is equal to 0, Xa is Xa1, and at Z is equal to Z, Xa is Xa2. Okay, you just keep these limits in mind. So from our previous slide, you have the differential equation, and now I'm integrating the differential equation, and for integrating I'm using this boundary condition. So on the left hand side you'll have integration from 0 to Z Na dz, that is equal to integration from Xa1 to Xa2 minus dAb, integration of minus dAb, let us put it in bracket, integration of minus dAb into rho upon Mw average dxa. Okay, so you get this equation. Now understood you, let us try to identify the constant terms. What are the terms that remain constant? So in the beginning itself we have understood that under steady state conditions Na is constant, molar flux of A is constant with respect to time, and if you are using DAB as the average of the best values available at the two ends of diffusion path, then you can take that as constant. And that is, if this is the average of best available values of DAB at the two ends of the diffusion path, then you can consider that as constant and you can take that out of the integral. Then average of this term, rho upon MW average, at the end of diffusion path, it is again considered to be constant. Average of values of rho upon MW average at the ends of the diffusion path. That average, it is considered to be constant and then you can take that out of the integral. So let us understand this with the help of this simple schematic, the profile which we discussed just now. So you have plane z is equal to 0, you have the plane z is equal to z. Diffusion is taking place from a point where concentration is xa1 to the plane where its concentration is xa2. Okay, so at this end, at the plane z is equal to z, there will be, if best value of DAB is known to you, and let me just explain. So let us say that DAB1 is the best available value of DAB at z is equal to 0, and DAB2 is the best available value of DAB at the plane z is equal to z. Then DAB is average of these two values. DAB will be DAB1 plus DAB2 upon 2. Simple average, arithmetic average of the two. Similarly, at this end, you will have one value of this group. Which group? Rho upon MW average 1. And at the other end, you will have rho upon MW average 2. Okay? And we are going to use the average value of this two. That is rho upon MW average. The average value is rho upon MW average 1 plus rho upon MW average 2 divided by 2. And this average value, we will be considering it to be constant. So we are now we have now understood that Na is constant, so it will come out of the integral. DAB is constant, so it will come out of the integral. In place of rho upon, if you use rho upon MW average value, that will be constant and that will also come out of the integral. Okay, so let us understand. Let us go to the next slide. Okay, so from our previous discussion, as we have identified the constant terms, now constant terms have come out of the integral, and now there is simple integration of dz from 0 to z is z with limits 0 to z minus dab rho upon mw average, and integration of dxa is simply xa as the limits go from xa1 to xa2, and in the next step, when you apply the limits, you get this equation. Na into z minus 0, that is equal to minus dab rho upon mw average xa2 minus xa1. And in the next step, you will multiply with this minus sign into the bracket. And if you do that, you will get Na into z, that is equal to dab upon mw average value xa1 minus xa2. And finally we can bring this z on this side and you get this equation. Kn is equal to dab upon z rho upon mw average, the average value xa1 minus xa2, and that is the final equation that you can use for calculating molar flux of A if there is equimolal counter diffusion of A and B. And the above equation, as I said, it gives steady state molar flux when there is equimolal counter diffusion. How to get molar flux for component B? It is simply minus NB, minus Na. We know this relationship and you can get the value for molar flux of NB. So in this way, you can derive an equation for steady state molar flux for a liquid when there is equimolal counter diffusion. I hope whatever I have discussed today is clear to you. If you have any doubts, you please mention that in the comment section. In my next video, I'll be discussing two numericals based on these two cases. Steady state molecular diffusion of liquid A in non-diffusing liquid B, the case I discussed in my previous video, and The second case, which I discussed today, equimolal counter diffusion of liquid A and B. So we will solve some numericals based on this in our next video. Please subscribe to my channel, tell your friends to subscribe to my channel and hit the bell icon. And if you have really liked the video, you please hit the like button as well. For time being, thank you for being with me. Hope to see you soon in my next video. Thank you and have a great day.